So our second speaker is Mehregan Doroudiani from University of Southampton, telling us about scattering amplitude of closed string at genus 1.
Thank you very much for inviting me. It's a pleasure to be here. So what I want to talk about today is the scattering amplitude, but for strings in string theory. The idea is the idea is basically the same as quantum field theory. We have a bunch of external states. They go to some scattering process, and yes, something comes out. So we have some in state, some out state. And to compute this, we also have this path integral. We have a bunch of fields. We have some kind of action. We have, for example, Polyakov action. And these external states are the boundary condition of this path integral. So it's basically the same thing that we have in quantum field theory, but everything here, all these things are defined within string theory. So what is it good for? The first thing is that the birth of string theory came out of some kind of scattering process. So it was a Venezian amplitude, and later on Virasoro and Shapiro amplitude, that it was not meant to be for string theory, but it gave birth to string theory, and everything started there. And also some years after, the first revolution of string theory also came out when people tried to study this amplitude at one loop. So it was at 3 level, the birth, and at one loop we had the first revolution. So one of the main reasons that we haven't heard anything after that about this scattering amplitudes of string is that anything that was possible to calculate was calculated almost here. And then after that, we did not know how to calculate things. So what I want to talk about today is some developments and some explicit calculations at 3 level and also especially at 1 loop. So one of the main reasons also to study these things is that they have very, very rich mathematical structure within. And the insights these things give us, for example, in motivic periods, is like wonderful, it's amazing. And we have learned so much from the 3 level amplitude. And what we would like to know is that what can we learn from 1 loop string amplitudes? We have learned so much so far, but there is much, much more to learn. We don't know much about what happens at 1 loop. And one thing is that all these insights and everything that happened at 3 level was after many computations, and people looked at the results of the explicit computations. They found some patterns, and then they found the reason behind those patterns, and many mathematical structures just came out. So we are kind of there, that we are doing these explicit calculations and we are seeing some patterns, but we don't know many of the things that happen as the underlying theory there. And of course, one thing is that after we have some amplitude, we can write some effective action. And effective actions are very, very important for string theory. For example, in type 2b, we have some dualities that even if we can compute something in a perturbative level, just by having the effective action, we can also talk about the effects of the instantons and many things like this. So we can also study the non-perturbative parts of string theory just by looking at the amplitudes of the perturbative parts. So the effective action is also very important. And of course, today I'm just going to talk about the flat spacetime. But if you go to compactified spacetimes, like if you look at, for example, ADS as a non-compact part of the spacetime, you can also see amplitude as some kind of tools for holography. But for 1 loop, we are not there yet. This is for future. So I'm not going to talk about this part. Okay, good. So what do we do? This is schematically whatever that happens in the perturbative expansion of the amplitude. So this G is the string interaction, and it comes in the path integral that we had here. It comes in the action as some kind of topological factor. So what it captures is the Euler characteristic of the worldsheet, and also the number of closed strings and number of open strings. And if we assume that G is very small, we can write some kind of perturbative expansion for it, and it would be some kind of genus expansion over the possible worldsheet of the strings. I will show you some pictures to clarify this. And whatever that remains in this path integral is, so some parts are the fields that we have as a conformal field theory problem in string theory. And some other fields are actually the metrics over the worldsheet. And doing the path integral over those metrics would be some kind of integral over Riemann surfaces, but punctured Riemann surfaces. I will talk about this one too. So yeah, so schematically it would be like this. So if I say that I have two closed strings incoming and two closed strings outgoing, the expansion, the perturbative expansion would be an expansion over all possible worldsheets. And here I just consider orientable worldsheets. So for example, it would be good for type 2b or type 2a string theory. Good. So another magic that happens in string theory, besides this nice genus expansion, is that if we take these external states to be asymptotic states, meaning that they go to infinite in time, in space-time sign, we can replace them with some vertex operators. And for example, here I have 4 states. So this would be something like a sphere with 4 punctures, and these punctures are vertex operators. So this is why I said that in the end we have some integral over punctured Riemann surfaces. So all these things, all these external states, you can just replace them with some punctures, and then you have some closed Riemann surfaces. So when I talk about 3-level amplitudes, I'm actually talking about this. So this is what gave birth to string theory. This is a Veneziano or Virasor-Shapiro. This is mostly. It's actually Virasor-Shapiro amplitude. And the main topic of my talk is something like this. So we have to find the CFT correlators over this, and then we have to do an integral over the moduli space of a torus with, for example, here there are 4 punctures, but there could be n punctures, and I mostly talk about 4 and 5 punctures. Good. Yeah. So we have M, G, and N as the moduli space of these worldsheets.
Can I just ask? So here is only closed string, you said.
Yes. I only talk about I only talk about closed strings. I mostly talk about one loop. I don't talk about 6 points and higher. I go at most to 5 points. And everything that happens is in a 10-dimensional flat spacetime.
And if I would like to add also the open one, how should I change these geometries?
So you could also here add, in these Riemann surfaces, you can add boundaries.
Okay.
And they would be open strings. Yeah, but so if you look at type 2 strings, there are no open strings. So you can just, so mostly I will talk about type 2 strings, superstrings. Okay, so this was the first expansion, which was the coupling of strings, and it would be a genus expansion. But I can also have another expansion, and it would be that I assume that the length of strings, or their square, which is alpha prime in string theory, I can assume that this alpha prime is very small. And what it gives us, for example, if you take this length to be very small, this would be something like this. And at one loop, it gives you something like this plus other Feynman diagrams. So at 0th order of this kind of expansion, it exactly gives us supergravity in 10 dimensions. And then if I do this alpha prime expansion even more, I get, in addition, the corrections of string theory to supergravity. So this is what I like in the end. Of course, this is not the only problem that you can study. For example, you can think about alpha prime being very large, and it would be the first people who studied that were Gross and Mende, but there are also some ongoing research about that. Also, you can keep it finite. But what I like to do is to look at this alpha prime expansion. Sometimes it's also called the low energy expansion. And I want to see what corrections it gives me in addition to supergravity. Okay, so the next thing that I have to talk about is that what are these external states? What are the possible states that I can have as external states? So now I want to also restrict myself to only massless strings. So in the end, it would be type 2b, 10 dimensions, massless strings. That would be my type. Mostly one. So what are these states? So we have a bunch of bosonic states and a bunch of fermionic states. And in type 2b, the supergravity, we have also an R symmetry, which is a U1 symmetry. But these states in string theory, they can have R charge. So this Q is the R charge. So we can have all these zoo of particles, let's say, or elements, whatever, states, with different R charges. And you can have any possible thing here. But there are two facts. One is that if you consider a combination with some R charge, if you consider two combinations with the same R charge, they can be related by supersymmetry or sometimes conjugation because of this holomorphic or anti-holomorphic. So I can only study one representation of this, and then anything else would come out from supersymmetry. So I don't need to look at all the possible states that appear. The second fact is that there is a bound on the maximum Q, maximum charge of the external states. Anything beyond that, you can see the amplitude vanishes. So if I look at four points for external states, the maximum would be 0. So there's only one state that I have to study, and anything else just appears from there.
Is this only at tree level, or?
No, it's not. It's at any loop order. So I only need to look at 4 gravitons at 4 points. And if I go to 5 points, the maximum would be 2. So if Q equals 0, I can look at 5 gravitons. If Q is 1, amplitude vanishes for several reasons. I don't have time to talk about it. And if Q is 2, we can have, for example, 4 graviton and 1 dilet. So these are the 3 types of things that I have to study. Okay. So let's go for a recap, just a very small review on genus 0. One fact about genus 0 is that you can write the tree-level amplitude for closed strings in this form. So what are these? So this is a vector of n minus 3, and n is the number of particles, external particles. N minus 3 states. So this is the 3 Yang-Mills, or actually super Yang-Mills amplitude. So I need two copies of the super Yang-Mills amplitude with some kernel here. And this pi and sigma are the different permutations of these particles. So I have to do a summation over all the different permutations. This is actually the double copy formula, if you're familiar with it in quantum field theory. Or in string theory, this is exactly the KLT formula. Because open strings are just something times one A Yang-Mills. And if you do that twice, it would be something like this with some kernel, with some KLT kernel. It would be something like this. So this is double copy because there are two copies of the Yang-Mills three amplitude. And these Sij's are the Mendelssohn variables. So this Ki and Kj are the momenta of external states. And so these states also have, for example, polarization because of the groove that they rotate on. And all these polarizations go inside this Yang-Mills three amplitudes. And whatever remains that and we have to compute is this S3, which is only a function of the Mendelssohn variables. So people started to do that for like 4 points, 5 points, 6 points. And it was something like this. So there is a universal factor, S0, which also captures the poles. And then everything else was like some matrices with multiple zeta values. These are the multiple. This is the definition of multiple zeta values. Multiple zeta values as coefficients. And these m's are n-3 times n-3 matrices. So it doesn't look like it has some pattern, but it does. And the pattern is so strong that you can write a closed formula for tree-level amplitude for any number of points. And to do that, there is an isomorphism between MZVs, multiple zeta values, and, well, actually, motivic version of MZVs, and some freely algebra of some words which are called the F alphabet, some Fs. So these F alphabets are, there's the algebra of F2, F3, F5, F7. These are all the numbers. And there's a map between Fs and these MZVs. And for example, this phi inverse takes us from F to MZVs. And if you write it like this, it would be this simple formula. And if you're familiar with this F alphabet of MZVs, you recognize immediately that this map, which this here is a shuffle product. This map is what Francis Brown found as a single valued map on multiple zeta values. So first of all, it tells us that all these MZVs that appear here are of a special kind, which is called the single valued multiple zeta values. I will talk about what single valued means for some numbers. And yeah, and the single valued map on Fs of Fi to Fp, Fi1 to Fip is something simple like this. So we have everything. And there's a way to find these M matrices for any number of points using Knizhnik-Zamolodchikov equations and Dirichlet associated. I don't have time to talk about this, but there's a recursive way to find all these matrices for different number of points. Perfect. So now we are going to genus 1. Okay, what's the moduli space of M1n? The way that we think of M1n is that we have a torus, and there's a vibration of the configuration of different points on a torus. So torus is something like this. So we have two cycles, and this is a famous way to describe it, torus. This tau is the modulus, and the torus has some moduli space, which is, for example, this fundamental domain here. And we can assume that there is a configuration space of the punctures fibered over this moduli space. So we can split this integral over the integral of the configuration space of the punctures, and then an integral over this moduli space. Again, easy. So yeah, so this integram, whatever appears here, would be the CFT calculations, conformal field theory calculations, and then the integral would be 1 over the position of these punctures and 1 over this fundamental domain. So we call this inner integral usually, we refer to this as integrands. So what are these integrands? What do we know about these integrands? One thing that we know for sure is that they are functions of this tau, this modulus. So they should respect the symmetries of torus. And torus has a large diffeomorphism, which is SL2Z. So whatever appears here as a whole integral here should be in a way that under SL2Z like this doesn't change. So it should be a modular function. This is the least that we should expect from this integral. And yeah, so also some small review on modular functions and modular forms. A modular form is a holomorphic function that under SL2Z, under the action of SL2Z like this, would change like this with some prefactor to some power, this to some power A. And this A is called the weight or holomorphic weight of this modular form. And also SL2Z has two generators, T and S. Also something else that we need, because we don't really work only with holomorphic functions, we actually work with real analytic functions, is a non-holomorphic modular forms. And non-holomorphic modular forms can have a holomorphic factor and an anti-holomorphic factor. So we have now two weights, the holomorphic weight and anti-holomorphic weight, A and B. So what are the, now the question is, okay, let's compute the CFT correlators and put it there and do the integrals. For n equals 4, you can find the CFT correlators in any string theory textbook. It's very easy, but for n equals 5, it's more complicated, and people usually use the pure spinor formalism for string theory. But anyway, both of them has been calculated. One many years ago, this in 2013. And so the inner integral, what we call integrand, looks like this. We always have this universal factor, which is called the Koban-Nielsen factor, and a bunch of other things. So this G here is a green function on the torus. And these other things are usually the derivatives of the green function. So we should first take the integral of some of this type of this sort of things. This is difficult, but in general, this is a very, very difficult integral. But as I told you, we can do this alpha prime expansion, which would be, so since there's an alpha prime in the S, which we can think of it as the perturbative variable here, and we can expand this exponential here. So if you do this, for example, at 4 points, we only have the Koban-Nielsen factor and nothing else. We would have such an expansion, and we can now integrate term by term. It would be very, very similar to Feynman expansions on quantum field theory. And actually, there is some kind of Feynman diagrams for each of them. So this 2 here means there are 2 propagators between vertices 1 and 2. So this is the number of propagators, and this is actually like this. This 2 here means there are 2 propagators between 1 and 2. And another example would be something like this, which would be something like this. So these things are called modular graph functions. And also, if you have derivatives of G here, they wouldn't be modular functions, but they would be modular forms. And there is a very, very nice and easy way to write them in some new Feynman rules. That if I give you a diagram like this, you can right away write some Feynman rules for it. So you can see this as momenta, as a momentum, this one too. It would be 1 over momentum squared. It's like Feynman propagator for scalars. But instead of integral, you have some summation. And you can also see this as momentum conservation at each vertex.
Sorry, what's the prime on top of this?
Nice. So prime means that m and n cannot be 0 at the same time. So the denominator cannot be 0. Thanks. Yeah, so many people started to work on these things. And these were very nice. And so for example, at one loop, people saw that, oh, these are non-holomorphic Eisenstein series that we had in mathematics. So nice. So they could be generalization of non-holomorphic Eisenstein series. And at 2 loops, the easiest one, the first person who solved a 2-loop one was Danzegier. It was, I think he wrote like 3-5 pages. And in the end, he found that it's a non-holomorphic Eisenstein series plus zeta 3, Riemann zeta function. So there is something very difficult happening here. And we should know these functions. And remember, in the end, we have to integrate these functions over that fundamental domain. So this would be a very difficult task. So also people started to look at these things more seriously starting from 2015. And they found many relations and identities among these MGFs, these modular graph forms or functions. It was very difficult to find a basis for them. For example, at 2 loops, at 3 loops, it's extremely difficult to find basis because not only the number of loops matter, also the number of propagators also matter. It's very difficult. And also, if you want to integrate them, so the person who is a master to integrate this type of lattice sums is Eric Docker. And he integrated as much as he could, but I don't think anyone can integrate more than he did from this type of things. So I never tried to go this way for integrating this.
By the way, originally, the Green's function is a Jacobi theta function.
Yes,
no?
yes.
So one has transformed the Jacobi integral into a sum.
Yeah. So the idea is to write the Fourier expansion of that Green's function, and integrating that Fourier expansion would be very simple. So the Fourier expansion would be something like this with some exponential in the numerator, and the integral over that numerator gives you these deltas. Very simple. Yes.
But
Okay.
G, here you have G squared. G is holomorphic and the Jacobi. So it was G star. Now we are non-holomorphic. No? At which point we get not, okay, Jacobi is, theta is holomorphic.
No, it's not just Jacobi. So this G is not holomorphic. In the end, this G is not holomorphic. It's yeah. Okay, but so okay. Now we need some way, some space of functions to classify this type of things, these MGFs, and that they would be suitable for doing any other calculations, computations, whatever. We know that they are modular forms. We know that they are real analytic. We also know that they are single value. That's very important. And we also know that if you act differential operators on them, you get something nice. So many of these relations came out when people just tried various differential operators on them. and they just solve some identities. So there should be something about differentiation and integration. But let's focus first on the single valuedness part. And again, let's go back to genus 0, because this is something that we know a lot about. So to write the amplitude for genus 0, the thing that we need, the space of functions that we need, is a multiple polylogarithms. It's like iterated integrals with D-log forms. And these A's can be zeros or ones. That's it. And they are multi-valued. So there are branch points at 0 and 1. So how do we construct a single valued version of these things? Because the things that appear in closed strings are single valued. One way to do that, the best way to do that, is to write some kind of generating series for them. So we have, again, a free algebra of two words, E0 and E1, and we make some kind of path order exponential like this, and it would be an expansion like this. And now it's very easy to find the monodromies. Monodromy around 0 would be like this, monodromy around 1 would be like this. And we want to write some kind of new generating series that kills all the monodromies, both over 0 and over 1. So over 0, for the monodromy around 0, the only thing that you need to do is to multiply by some kind of complex conjugate. And that's it. The monodromy disappears. It looks very, very much like the simplest example is, for example, log of z. This is multi-valued around 0, but if you add log z bar, then this could be log z2. This is single value. Great. But around 1, it becomes more difficult, and you need to add another element, a new generating series. So this new generating series, if you add it, it must satisfy these two equations. And it defines something that is called the zeta generator. So if I expand this M0SP, there would be an expansion like this. These are all of these are single valued MZVs. If you write it in terms of those F alphabet, it would be much nicer. And these M's would be zeta generators. Well, they are called the zeta generators. And they should normalize the free algebra of E0 and E1 like this. Okay, perfect. So if we write this type of things in genus 0 in terms of zeta generators, then there is a way to do a single valued map on them. And by the way, so we can extract zetas from these G's, from these these multiple polylogs. And also you can make multiple polylogs single valued. So if you extract zetas like before from single valued multiple polylogs, they are called single valued MZVs. They are called single valued multiple zeta values. So this is where the single valuedness of the numbers multiple zeta values come from.
For instance, the single values dialog is what?
I don't remember. There's
not Widner dialog.
It is just this, because there are several versions, no, of the good.
Well, you can have some multiple of these log squares.
Yeah. I don't remember the formula, but it's it's also the depth
The blocking
two
is
thing.
the imaginary part. So it's now I forgot there is a real part, imaginary part. Here it was just the real part.
Yes.
But it's not always the real part.
Here they're all real. So it would be either the real or part of the imaginary part of the
They're always real.
Yes, these are always real. Yeah, okay, so we should do something similar for genus 1. But remember, now we also have a symmetry on genus 1. We have the modular symmetry. So for that, the kernel of integration of these iterated integrals would be holomorphic modular forms. And for example, we can use holomorphic Eisenstein series like this to make the iterated integrals. And all these are holomorphic modular forms with holomorphic weight k. And again, we make a path order exponential of this. But here, so these epsilons are analogous to E0 and E1. But here, these epsilon k's are not free anymore. There are some relations between them, and there's each epsilon k is also a representation of SL2 algebra. I don't have much time to explain this, so I'm going to skip this, but I would be very happy to talk about this later if you want. So yeah, so these are called the Tsunogai's derivation algebra. It's a derivation algebra that acts on the pi1 on torus, of torus. And again, we have T transformation and U transformation. And we should write some kind of generating series that in the end gives us something covariant under U and T. Let me skip this because I don't have much time. But again, something comes out of these calculations, which is called the zeta generators, but this time for genus 1. These sigmas are the zeta generators. And they also normalize the algebra of epsilon k. But these epsilons are not inside the algebra of epsilon k. And anyway, in the end, we can write a generating series that is called the equivariant generating series. So this is modular and single value. This is exactly what we need. It would be like this. This z is the part of sigma that is not inside epsilon. I will talk about it later if you want, but I don't have time to talk about the. Yeah.
No, so the series M is the same as before, but you.
But that time was for M.
Yeah.
But this time is for sigma. So yeah, M was the zeta generator for genus 0. Sigma is the zeta generator for genus 1. And you can see that, for example, if you go back, if you take the limit from genus 1 to genus 0, sigma goes to M. There are so many nice features here. But anyway, so one of the progress that we had in the past years was to construct these things. The first idea was from Francis Brown, and then we worked out everything explicitly for any number of iteration in the integral. So these are the functions that appear out of these things are called equivariant iterated Eisenstein integrals, or EIEIs. And modular graph forms are a subset of these functions. So again, these functions, they have all the relations of these modular graph forms manifest in them. They do have some kind of canonical basis. And also they're more suited for integration, well, especially because they are themselves some integrals. They're not some lattice sum representations.
Is it modular graph forms or functions?
It gives you any modular graph form. So modular graph form is a generalization of modular graph function.
And these things were single value?
Yeah.
And do we expect that the modular forms are... So these things that you constructed, they're not modular invariant, they're covariant?
No, yeah, they're modular covariant. Yeah. There are all the possible modular forms in them. So yeah, so this is also very, very important because we know almost everything about holomorphic modular forms. But for non-holomorphic modular forms, they're not much known. And people need to look somewhere for them because their space is so vast. And these EIEIs are a very big class of non-holomorphic modular forms, which is extremely interesting. So yeah, so this was one of the ideas that string theory gave to mathematicians or something to study. Okay, so at some point we have these EIEIs, at some point we have these modular graph forms. But how do we translate between these two? How do we, if you give me a modular graph form, how can I get some EIEI? The idea here is very, very simple. So if you didn't follow the algebraic part there and single value part there, this part is very simple. So let's say you give me a modular graph form. I start to act this derivative, this mass derivative on it. And I get different terms. Some terms are some modular graph forms times holomorphic Eisenstein series. Some terms are without them. Whatever, I can have many, many different terms.
A and B were the two weights of the non-holomorphic modular form as weights under A tau plus, or C tau plus D and C tau bar plus D.
Yes.
These are A and B's?
Yes. So this is the holomorphic weight. This is the
so there are really non-holomorphic forms in that A, C, D, A, B.
Yeah, so these are non-holomorphic modular form. So yeah, so this nabla, what it does is it takes a non-holomorphic modular form of weight A and B, and it gives something with weight A plus 1, B minus 1. So we act this nabla on this modular graph form. It gives us more modular graph forms, but some of them are multiplied by this GKN. So everything in the same row, you should add them. And if there's a G next to a vertex, it means you have to multiply them.
And here G are the Eisenstein holomorphic things.
Yes, these are the holomorphic Eisenstein. So for example, these ones. So this is 1, 2, and 4 vertices. So here I have 2, but let's say I have 4. So this would be very, very difficult in the lattice sum representation. But if you act this on it once, you get another not interesting modular graph form. If you act it twice, you get a non-interesting one, but you get another interesting one, but with a G4. And then you do this over and over and over again until the only thing that you get is holomorphic Eisenstein series. So the reason that such a tree exists, and it exists for any kind of modular graph form, is because of the EIEIs. It's one of the features of EIEIs, and we know that MGFs are some subset of EIEIs.
So you reduce A or B to 0 here to have something holomorphic at the end?
In the end, we reduce one of them to 0 to make it completely holomorphic. Yeah, we reduce B to 0. And then now we have some G's, and now we should integrate back up. So we took the differentials, we went down, now we integrate back up. But we don't actually need to integrate, because we know that these functions in the end are functions that come out of EIEIs. So we look at the functions that appear in EIEIs. These are called beta equivariants. So this, whenever it is like 1 to L, it means there are L number of iterations in the integrals. So this is actually L integral. And they satisfy such a differential equation. And we can see this. So here you see G times some beta. So if here I have G and no beta, this beta would be a beta of like nothing. And then I have some right-hand side for this differential equation, and I find the left-hand side. And then I go back up and one by one. So it would be just a linear algebra problem. It wouldn't be actually a very difficult problem. And one thing that we did we made a package that does this algorithm, this going down and then going back up for many, many number of modular graph forms. So, okay, so in the end, we have everything in terms of these beta equivariants. These beta equivariants are the functions that appear from EIEIs. And you can write any MGF in terms of.
So this differential operation has no kernel. Going back is 1-to-1. Right?
Okay, it is not. It's almost 1-to-1 because of the modularity. So these beta equivariants are also modular forms, and it restricts going back up a lot. So the only time that there is something that we can add is that one of these vertices is a modular function, is modular invariant. You can add a constant to a modular invariant function, and it still is a modular invariant function. So for example, here, this one is modular invariant. So yeah, so we have this problem that there are some constants that you can still add to this process, and constant goes all the way up, and then you have to somehow do some Fourier transform on this, get the zero mode, and fix that constant. Yeah, it's one of the problems of this thing. Okay, so now we can expand everything here in terms of these beta equivariants. But now we have to do the other. We have to perform the other integral. How much time do I have? 15. Yeah, okay, it's okay. I don't insist on finishing the talk because there are so many things here. So there is one problem if you want to take this integral. And the thing is, here we did a Taylor expansion for the low energy limit. But this Taylor expansion, if you do that, it fails. The Taylor expansion fails near the cost tau goes to infinity. Especially because we know that at one loop we have monodromies for the amplitude because of unitarity. So, for example, we have logarithmic terms, and there's no way that you can get the logarithmic terms by doing a Taylor expansion on these things. So if you want to do the Taylor expansion, you're not allowed to do the integral over the whole thing. You must put a cutoff, do the integral over that part, and for the upper part, you shouldn't do the Taylor expansion. The thing about this part is that at least the region is simple to integrate. It's just a rectangle. But the bad part is that you cannot do an expansion over this part. You should do this part exactly. For 4 points, this part is done by Eric Doker and Michael Green. But for 5 points, it's still an open problem. So we don't know the integral over this part for 5. So whenever we have major graph forms expansion, we should be careful that we should put a cutoff and we should integrate up to this cutoff. Good. So how do we do the integral over this fundamental domain with a cutoff? One nice thing about EIs is that they satisfy some sort of Laplace equations. And the reason is also because of the representation theory of those epsilons. I will talk about it later if you want. But the thing is, usually at each iteration depth, you have two sort of functions. One is the product of things with lower depths, with functions with lower depths, and some functions that you cannot write them as products. They are the new functions. But these new functions, you can always find this type of equation. An equation like this. So if I have an equation like this, and if I want to integrate this f over this part, I can write the integral like this, and for this part, I can use the Stokes theorem. And if you use the Stokes theorem and use a modularity, the integral over this part, this boundary cancels out, and it would be only an integral over this part, which gives us the zero mode of f. So if mu is not 0, it would be very easy to integrate f if I know the integral of this. So if mu is 0, I have a problem. Okay, now how do you find the integral of the right-hand side, where we do not have the Laplace equation like this? For that, we usually have some sort of Poincare sum representation. This gamma infinity is a Borel subgroup of this SL2Z. And if I find another function, small f, which is called the seed function, if I find a function like this, that I can write f as this type of summation, then again, it's very easy to write the integral of f. The integral would be like this, and this 0 means you have to find the zero mode in the Fourier expansion of them. And tau2 is the imaginary part of tau. So I either should have the Stokes theorem, or I should have some kind of Poincare sum representation. usually when you don't have a Poincare sum representation, you can force it to have a Poincare sum representation, because if you use the non-holomorphic Eisenstein series, it would be like this. And so you can multiply Eisenstein series on your function. You can unfold it, and then if you take S to some S to, for example, 1, it would be the constant. So it has a pole, but the residue would be a constant. So you can force your function to have a Poincare sum representation. But then the problem is that that representation, that summation is not convergent anymore. And then you have to be lucky that you have some sort of analytic continuation for that.
You mean minus S in the exponent?
Yes. Sorry. And we were lucky almost everywhere except for one function. So these are the actually these are the only techniques that we know on how to integrate over the fundamental domain. There is no other technique that analytically gives us something. And yeah, I have done this for anything up to iteration of depth 3. Beyond that, I cannot do that. I don't know any way to do that. So I would be very happy if I find some way to do that. And then we can use all this data to actually compute the amplitude. So the first part, the integral, the integral over the configuration space, we solved it by using this EIEIs. And the second part, we use some techniques. And yeah, let's put all this together and see what happens. So again, for 4 points, we can also write it, write the result of the amplitude as this double copy thing. And this A Yang-Mills, in the end, captures all the polarizations of the external states. And we have to find this S matrix. So perfect. So it looks very, very much like what we had for 3 level. So this S0 is the same, is exactly the same. These matrices M's are exactly the same. And this pattern is also exactly the same. The only thing that changes is that these coefficients are now the integrals of this MGS. So it's very nice that it's almost exactly the same thing. And for example, you can find the coefficients here. You don't need to read this. The only nice feature about this is that is the numbers that appear here. So before, for 3 level, we only had multiple zeta values, single valued multiple zeta values. For 1 loop, again, we have single valued multiple zeta values. But we have something more. We have the logarithmic derivative of MZVs. Or, okay, here of only Riemann zeta value. So these are the new numbers that appear in the amplitude of string theory at 1 loop. And these are not periods. That's very important. And the pattern that arises for these new numbers that appear is that the sum of the coefficients is -1. The sum of the coefficient everywhere is -1. Why? We don't know. And so the coefficients are going to get much, much worse, but still the sum would be just -1.
Sorry, capital N was the cutoff on the.
Was the cutoff? Yeah. So this would cancel out in the end. We usually don't write anything L dependent because we know that it cancels out in the end. We only take the logarithmic part because the coefficient of the logarithmic part is exactly the coefficient of the logarithmic part in the Mendel steps. So it has, so the logarithmic part has some data for us.
Funny that in the last one, the Euler gamma doesn't appear with the same coefficient as the log.
Yeah.
That's the axiom, I guess.
So yeah, so I can talk about the patterns in the number theory part more, but let's move on. Because I also want to...
is zeta prime 1 over zeta 1, or it's a regularized value.
Perfect. Yes, I will talk about that. Yes. Yes. Perfect. So yeah, so this Euler mascaron is also not very different from this thing. And by the way, so these are only at odd integers, so positive and negative odd integers. If you, of course, you can reflect them and write them all in positive, so it would be odd and even. But if you do that, many bad numbers appear that you don't like. So many like log of pi's, log of 2 pi, and more gammas, things like this appear. So it tells us that, okay, the best way to write it is in terms of odd. And actually, a mathematician, Vincent Maillot, gave us this insight. He suggested to do that. We did that, and everything just simplified a lot. Okay, so let's go for 5 points and this sector that the R symmetry is not violated. Again, we have the same pattern. We have the same things, the same matrices, the same M, the same S. But now we have some new matrices as well. So M prime, M8 prime, double prime, triple prime. And it has some meaning in the effective action. I will talk about it in a minute. And yeah, and then we can go and read this, read these coefficients of the matrices, and we can also find these matrices. Yeah, okay. I also talked something about the factorization, but let me not talk about that. If you can, I can talk about the factorization of 5 point to 4 point later. And these are the size. Again, you don't need to read it. But as you can see, so these are the coefficients. Again, the sum is -1. And we see the exact same numbers as before, but we have a new number. This is the function that I could not integrate. This is the only function that up to depth 3 I could not integrate. Also, because of the thing that you mentioned, that we have some constants, we usually can fix that constant by some techniques. For example, by looking at the UV divergences in the KFT one loop matrix elements. But there were some parts that we could not find this constant. These are rational numbers. So yeah, there are some parts, there are some constants that are not fixed. But anyway, so this omega is actually a new number that we have no idea what it is. We tried PSLQing with this type of numbers, with zetas, nothing works. And yeah, so okay, so there are some nice features. For example, the highest weight of zeta always has uniform transcendentality, and the other ones, the coefficients add up to -1. And as you mentioned, we can also see gamma as the regularized zeta prime over zeta at 1. So it appears that the new numbers that we need are these d-logs of zeta n. But also this new number, we could find it numerically. We have a way to find all these integrals numerically. I can also talk about that later if you want, but I don't have time to talk about the numerical integration. So we know it numerically, but we don't know what it is. And yeah, and also we have the result for maximally R violating. So if I have like 1 or 2 minutes, let me also talk about the S-duality and what the amplitude does for the S-duality. So the thing is, the moduli space of type 2B string theory is this. And if you're familiar with this, you know that, oh, okay, this is this can be characterized by some complex structure, and everything in the theory can be written in terms of this structure, and it should be, and we would have the SL2Z symmetry for our theory. So this structure can be written as the axiodilaton. So this is the axion, the Ramon 04, and this phi here is a dilaton. And if you write all the operators in our action in terms of this, we again have another kind of SL2Z. So this has nothing to do with the SL2Z that we had so far. That was for the worldsheet at one loop. This is for the whole theory. So this is what it's called, the S-duality of type 2B. And for example, if I write an effective action for type 2B, so this is the non-string theory, so this is the supergravity, type 2B supergravity, and these are the action that string theory adds. All these terms here, they should be automorphic forms or modular forms of SL2Z. And for example, E3 and E5 can be written in terms of non-holomorphic Eisenstein series. What it tells us, so the non-holomorphic Eisenstein series, all these automorphic forms, they have a zero mode. And if I put the zero mode here, and if I just look at the zero mode, it gives me an action that I can look at its amplitude. And the tree amplitude of this action would be the amplitude of the string theory that I found. So the amplitude here would be very, very useful. I just look at the amplitude of the string theory and I write an action that gives me the same amplitude. By the way, this R here is the Riemann curvature. So if I find and also these coefficients are exactly the coefficients that the perturbative amplitude gives me. So I read the perturbative amplitudes, I get these coefficients. I know that the whole thing must be modular form. So then someday I can have some information about the non-zero modes, which are the instanton effects. So this is why a perturbative expansion of the amplitude is important. And furthermore, now that we have new amplitudes, we can tell the people who work on the S-duality that, so this is the supergravity, this is anything else. We can tell people that, oh, okay, you should find new operators, new interactions at this point related to these terms. And all these things must be automorphic forms of SL2Z. And their zero mode must be the amplitude that we found.
Most of these are not protected, right? They're not one.
No. Yeah, after this, it's not protected.
So you should have other perturbative contributions before the instance. And those...
they all contribute, but so you can have some arguments based on the weight. That's so you don't need to look at everything and like this related to this one, this one. So there are some arguments.
But this will break at some order, or you can always guess based on the leading term what is the completion.
No, you can't.
Okay.
But at least you have the first one. Yeah, and the automorphic form that you should find must have this as the leading orders, and they should have d log of zetas in them, for example. It would be, can you find such an automorphic form? And so what we do is that by this calculation, at least we can predict these new automorphic forms and these new interactions in type 2B. And this is also the same for the maximally R-violating segment. And that's it. Sorry it took all our time. So the thing that we want to do next, the first thing that we are working on is to determine those rational numbers. And just let me tell you, so the idea is that just forget about the MGFs. If we have some generating function for the amplitudes themselves, we can just go and look at the part in the generating function or generating series, whatever, that gives us the amplitude, and we can read that right away. This is what we are going to do next. To just forget to see everything in terms of the AEIs. Do not go through the MGFs and go back to the AEIs where we cannot find these rationals. This is a work in progress. Also, we developed this numerical method to find all the numbers for this integral. So at least we can try to have a big numerical data of the things that we cannot find. And also, the only things that I talked about here was superstrings, it was type 2b superstrings, but it would be the heterotic strings are also very, very interesting. And we have weakly holomorphic major forms there, and not just non-holomorphic major forms. And this is also something that we are working. Yeah, thank you very much.
Maybe we have time for a quick question because we're running a bit late. If not, let's thank Mehregan again, and we continue with our last speaker.